Good evening, and thank you for joining us for the August edition of Thought Leaders, Space Center Houston's monthly lectures designed to ignite your curiosity and grow your passion for science and space. I'm Dr. Susan McClellan, a specialist in infectious diseases and special pathogens with UTMB Health, proud sponsor of this series. Tonight, we learn about Argos, NASA's training and testing system that simulates reduced gravity environments. It's a fascinating topic, and I look forward to learning more about it. However, before we go there, we want to take a moment to remind you that the dangerous Delta variant of COVID-19 is spreading rapidly in our area. UTMB and the region's healthcare providers are seeing younger and sicker patients, including children and pregnant women, in need of serious care. Our hospitals are full. Many have died. We need your help to stop this virus in its tracks. Fortunately, we have the tools to do that. Get vaccinated. The vaccines are free, safe, and will keep you out of the hospital. Wear a mask, regardless of your vaccination status. And finally, get tested if you feel sick. Early diagnosis increases your chance of survival. Remember, by following these recommendations, you can save lives, a loved one's, a stranger's, even your own. Once again, thank you for joining us tonight for the Thought Leaders Lecture Series. Enjoy the presentation, and please stay safe and healthy.
Hello, I'm William T. Harris, President and CEO of Space Center Houston. We're a dynamic science and space exploration learning center and nonprofit science center. We're also the official visitor center for NASA Johnson Space Center. We share the story of human space exploration, past, present, and future, with more than 1.25 million visitors every year from around the world. Thank you for joining Space Center Houston's Thought Leader Series, Neutralizing Gravity on Earth, presented by the University of Texas Medical Branch. Our Thought Leader series brings you space and science experts from around the country to provide insights and perspectives on space exploration. Space Center Houston provides robust learning experiences for you to be part of the NASA mission. This summer, our exhibits and programming are themed around pushing human limits. Guests are afforded a rare look at how astronauts are training for human exploration for travel to the Moon and Mars. You can discover how astronauts train on land, underwater, and beyond. Only Space Center Houston takes the general public behind the scenes to NASA Johnson Space Center, the home of astronaut training. Our new exhibit will be open through September 6th, and it's called Beyond Human Limits. You can save time in line with advanced time admission tickets, and you'll experience our most popular behind-the-scenes experience, the NASA Tram Tour, which takes you to various facilities at NASA Johnson Space Center, including the Astronaut Training Center. Plan your journey with us today, purchase your tickets in advance, and save time in line at spacecenter.org. Today's program focuses on how gravitational forces vary significantly from Earth to the International Space Station to the Moon and Mars. In order to prepare astronauts to work in a variety of environments, NASA must continuously develop innovative training systems. Right here in Houston, NASA Johnson Space Center is home to the Active Response Gravity Offload System, or Argos. It simulates reduced gravity environments. We'll delve into this unique training system in our August Thought Leader series presented by UTMB. And now on with our panel, Neutralizing Gravity on Earth. It's my pleasure to introduce our panelists. Our Thought Leader series panelists include Paul Valle, Argos Project Manager at NASA Johnson Space Center, Jocelyn Dunn, Human Performance Engineering at KBR, supporting the NASA Human Physiology, Performance Protection and Operations Laboratory, and NASA astronaut Mike Foreman. Our first panelist, Paul Valle, oversees Argos operations for human testing and leads the development of the future next generation Argos. As the project manager, he interfaces with internal and external test and training customers for Argos, leads the operations team that operates the system, and leads an engineering team to develop the next generation human-rated Argos. Our second presenter, Jocelyn Dunn, serves as the technical lead for the spacesuits and exploration operations technical area of H3PO. This team supports astronaut training for extravehicular activities, or spacewalks, physiological data analysis, and modeling to support EVA planning, and lunar analog testing of next-generation spacesuits, tools, and concepts of operation. Prior to joining H3PO, Jocelyn worked as a research scientist for the NASA Cardiovascular and Vision Laboratory, managing and analyzing data from bed rest and ISS flight studies. Our third presenter is Mike Foreman, a retired astronaut. He was selected as an astronaut in 1998. A veteran of 2 space flights, he flew an STS-123 in March 2008 and STS-129 in November 2009, and has logged more than 637 hours in space, including 32 hours and 19 minutes on 5 spacewalks. Following his own astronaut candidate training, he was assigned technical duties in the Astronaut Office Space Station branch, representing the Astronaut Office on training issues. Mike was assigned to the Exploration branch, working on the Commercial Crew Development Program. During his final 3 years at NASA, he served as the Safety Branch Chief in the Astronaut Office. Our panelists will now each provide more information about their backgrounds and the scope of their work, and then we'll have a great conversation. So welcome, Paul, Jocelyn, and Mike. We'll begin with opening remarks by Paul.
Thank you, William. It's a pleasure to be here. So as William mentioned, I'm the project manager of the Active Response Gravity Offload system, which means I oversee that system at the Johnson Space Center. And with this presentation here, I'll walk you all through why we need Argos and how we use it, and then what the future looks like. So the first question is, why do we train and reduce gravity? And the real reason is to reduce the risk to our crew safety and health, and reduce the risk to mission success. And this pretty humorous video of Apollo astronauts on the moon highlights why it's sometimes pretty difficult walking in reduced gravity, whether it's in lunar gravity or microgravity. Moving around is a lot different than how you spent your whole life on Earth. And by using reduced gravity training systems, we can better understand and train for the environment to try to avoid this from happening, where you might not be able to get up easily, or you might have a lot of difficulty doing a task or taking a sample. We can design our hardware much more efficiently, whether that's the spacesuit, the tools, the geology sampling devices that a geologist might be working on. Anything that needs to be used in that reduced gravity needs to be designed for that. And then we can better understand our human performance during that EVA, so the astronaut doesn't fall over while they're throwing that bag. And so we do that with a few different systems and ways at NASA. The first of which is often seen. It's our large pool. It's the NBL, or Neutral Buoyancy Lab, and that's a huge space. We get a lot of EVA time out of it, of a simulated spacewalk. It is underwater. We can put a lot of people in at the same time, and we can make the tools weightless. The second one we've got is Argos, which we'll be speaking about today. That's a large space. We can also do long EVA time, no underwater environment. We get high dynamics and fidelity. And we can do an on-the-fly gravity adjustment. So we can make you go from lunar gravity to Martian gravity in a matter of seconds very easily. And the third way typically is reduced gravity aircraft. It's a much smaller space. You're in the fuselage of an aircraft. Short weightless time because it's at the top of a parabola. There's no underwater environment as well. It's got the best dynamics and fidelity since it's truly microgravity or lunar gravity, and you can tune it by that parabola. And everything in that fuselage is weightless. So all the tools you might want to be using are all weightless as well. But today, again, we're going to be focusing on Argos and what it is. So the Active Response Gravity Offload System is a robotic simulator that simulates reduced gravity for people and other payloads. It looks like an overhead crane, as you can see in this picture. This blue structure houses Argos, and the yellow rails that go across is the actual Argos offloader system. And it senses what the person or the payload below it is doing, and then actively responds to their motion to maintain that simulation without an operator ever intervening. And so this way, once Argos is offloading you and providing that weightless or lunar gravity or Martian gravity simulation, everything you do, you feel like you're in that reduced gravity environment. So how does Argos work? The real basic principle is, if we look at a suited astronaut on Earth and say, assume that they weigh 600 pounds with their person, their suit, their life support system, everything they're carrying, they feel 600 pounds of ground reaction force when they're standing there. If we take that same astronaut and spacesuit and life support and put them on the moon has 1/6 the gravity of Earth, which means they feel like they weigh 100 pounds on the moon. So then when we want to simulate that in Argos, what we do at the most basic sense is we lift up 500 pounds using Argos so that they still feel that 100 pounds of ground reaction force. And if we want to put them into microgravity, we lift up 600 pounds so that they are floating in the system. Now, getting into a little bit more of how we do that, Argos really does two key things. It provides a dynamic vertical force to offload either all of or some of something's weight. And when we say dynamic force, that means it's always adjusting that. So if something pushes up a little bit, it moves up so that it's still trying to offload that same amount of weight and hold that same cable tension. At the same time it's doing that offload, it also provides horizontal motion to maintain that vertical offload force, actually vertical, while also providing natural kinematic motion. And by that, I mean, if you push off in Argos in any direction, when you're in microgravity, Argos allows you to continue to float in that direction, just like you would in space. So the horizontal system is both trying to respond to those disturbances and also maintain that natural coasting motion so that you truly feel like you are floating in space. And this also helps us in lunar and Martian gravity in best simulating that environment. We achieve this motion by using sensors to measure the force in the lifting cable, the angular displacement of that same lifting cable, and measure the current motion state of the system. And all of that feeds into a computer control system that can then respond to those inputs with commands to electric servo motors and all three axes of motion and drive the system around in response. And we do that at a very high rate of speed. The computer is constantly sampling the environment to make sure that it's getting the right output. All these sensors as well are internal to Argos. We're not using motion tracking, vision, anything else. These are all internal to that crane type system that we've got here circled. So how do we compare to those other methods I talked about earlier? So we're a complementary simulator to the NBL and reduced gravity aircraft. There's no one simulator that is perfect for simulating and training reduced gravity, and all have benefits and drawbacks that we use at NASA in a complementary format so that we can get our best training in. The benefits of Argos are that there's no water drag. Since we're in an open air environment, we have no drag that you're feeling. You're not swimming through the water ever. When you push off, as I mentioned, you can keep floating. If you're underwater, you come to a stop because you're underwater. So we get the most accurate dynamic movements, especially if you start trying to move really quickly. I don't know if anyone's ever run in a pool, but I know that's a lot of work trying to run down in a pool. I don't like doing it, so I like doing that in Argos a lot more. The lack of water depth also reduces the chance of decompression sickness during suited testing because we're not doing large-scale pressure changes if we have to simulate moving in a large direction. And then also it's easy to get our engineers, our scientists, other crew members, other technical folks in quickly for proof of concept testing. There's very little overhead to get them harnessed up into the system and understand the environment they're designing for. The drawbacks, though, are that our rotational degrees of freedom are less realistic. And I mean that by rotating your body in various orientations is hard because we're lifting you with a cable. So we have to simulate those rotations with gimbal devices that we harness you to. And then the subject is still in 1G inside the harness or the spacesuit, and everything else in the environment is still in 1G. And we mean 1G by Earth's gravity, which means if you drop a tool, it's not going to stay floating next to you in microgravity like it would in space. It's going to fall to the ground. And if you're in the suit, you still feel yourself kind of sinking into the suit a little bit, even though your whole suit person system is offloaded to that gravity. Our key specifications, we have about a 12,000 cubic foot test volume. We have vertical speeds that we can do up to about 10 feet per second and horizontal speeds up to 6 feet per second, which is about a light jog. We have vertical accelerations up to 80 feet per second squared, so it can support a very rapid athletic jump, and horizontal accelerations up to about 20 feet per second squared. We can lift up to 750 pounds, which gives us plenty of room to lift a person, spacesuit, tools, gimbal, life support, all those things that we need to do full EVA training for. And at the same time, we have an offload sensitivity down to about 1/1000th of a pound. So what I mean by that is if you add 1/1000th of a pound to something that's being offloaded by Argos, it will very slowly start drifting down with a very imperceptible thrust, but eventually end up down. So we are quite sensitive, even though we can offload that much weight. As far as the history of Argos goes, we started designing the system in 2007. And started our first human testing and training really to understand what we needed to do to create a real training device with that system. And so you can see a subject here that's actually myself on an early version of Argos running on a treadmill, trying to test out the sensitivity. We then went to what we call Argos 2A in 2011, using all that data from that first prototype to make a much more ready to train system that was much more capable in what it could do. And in 2016, released Argos 2B, which further added to the safety and performance of Argos 2 to continue Argos as a true human testing and training system. So now that we're running Argos 2B today, what do we use it for? One of the areas is crew training, and we'll regularly put crew members in to train specific tasks for the space station today. We also do a lot of human research and performance studies, both for microgravity as well as future lunar and Martian gravity. We do engineering development on tools, spacesuits, exercise equipment, all sorts of things that our engineers at JSC are designing for use in reduced gravity. We do robotics development where we put robots, whether they're small rovers or Robonaut 2 or other robots, into Argos to simulate reduced gravity for them as well as people. And then we use the system for outreach as well occasionally, and trying to use it to communicate how working, living, and all those things we do in zero gravity or in lunar gravity are different than here at Earth. So next, I'll walk you through an example of really a deep dive of how we've used Argos recently. And this is to support the AMS repair development and training. So the alpha magnetic spectrometer, or AMS, is an experiment on the exterior of the International Space Station that detects antimatter and cosmic rays. By 2017, only one of its 4 cooling pumps were fully operational, so it's past its original design lifetime, still giving good data, still wanted to get more data out of it, but it was not designed to be serviced in space. The payload itself is extraordinarily sensitive. It's detecting, these very precise things coming from deep space, so it's not the easiest thing to work on, not just like working on your car in a garage. So it took about 4 years of planning that led to 4 separate EVAs in the 2019 to 2020 timeframe that were the most difficult since the Hubble repair. And so we started with Argos by putting astronauts, engineers, tool designers, hardware experts into the system to have a very early look at what was feasible. And we took a mock-up that had a high fidelity section for it that you can see here with those cables going into it in the silver part. And we made it so we could both stand it up so people could work on it really easily, as well as lay it down so that we could then test it with a test subject in microgravity in Argos. And what we were able to do is right off the bat get all of the engineers that were tasked with designing the tools and the procedures and the concepts for how we're going to fix this into trying to actually fix it with commercial tools, 3D printed tools, other things, and gave them a very early look to just understand the task that was ahead of them. And so as you can see in this picture and the next picture here, we could also put all the hardware experts right alongside them. And so you can see this tool engineer talking with a hardware expert and crew training people, trying to walk through what they're doing to understand how best to start going off in design. And we could have them try out a 3D printed concept. We could then have them re-3D print that concept with a new design, maybe that night or the next day, and then put them right back into Argos from there. Next, we added in putting crew members in and starting to really get an understanding of these high fidelity areas. Also shirt sleeve, as you can see, we're not wearing a suit yet, just so we can really get that understanding again of what was even ahead of the team. And the key with Argos is because we were in the open air environment, we were able to have that mock-up be something that could be reconfigured very rapidly by the team, as well as be its full fidelity. Those stainless steel tubes weren't really something that you could leave under the water for a long time with water compatibility issues, as well as all the stuff that goes into reconfiguring it after an astronaut comes through and cuts all of those tubes to start practicing and trying all the new tools. You can't just send somebody down to the bottom of the pool very easily to do that. So they are able to do that in Argos. So from there, we moved on to suited testing and put astronauts and other test subjects in to still keep working on those tools, because using them with a suit is much different than doing it just in shirt sleeve environment. So the tool design kept increasing in complexity, getting more towards final designs. We also did night operations to help make sure that the astronauts during the night cycle, when it was dark on the space station, could see. We turned off all the lights in the building and let them go through the whole repair operation using just their headlamps. It looks incredibly real. I can say from experience, when you're standing there and you see an astronaut floating in Argos with their headlights on as they're working on all these real tools. And then finally, as we got closer and closer to the mission, we put the actual astronauts that were going to be performing the repair, both in spacesuits and plenty of shirt sleeve runs, to do their full training on the final repair operations and the final procedures. You can see astronauts Luca Parmitano and Drew Morgan here doing some of their final training runs in Argos. Occasionally, the things we do look a little goofy. You can see those foam cutouts on his helmet, and there's actually one on Luca's chest as well there. We're doing that to help simulate some of the volume constraints of the spacesuit. Just for timing reasons, we had to go in shirt sleeve for these runs and these training runs, but the whole team was looking at to see if those foam pieces touched anything, because that was an indication he was getting too close to the hardware. And next we have a video of Luca Parmitano during that training run. And you can see his feet are in what's called an APFR. That's the foot restraint that would be outside of the space station so that he can have a more stable platform to work. And here he's using some of the final flight design tools, the ground versions of those, to do all of the tasks that he was going to have to do for that repair. So this is one of them where he's unbolting some of the hardware on one of these covers. And he's able to feel like he's weightless, react all his loads through that APFR just like he will be during the mission, and get a really great understanding of all the high fidelity hardware in that relevant environment. Again, truly cutting down on the risk to mission success by having him able to do this in that full fidelity. So next we have a video of us using Argos for xEVA development to support the future Artemis lunar landing. And what we're doing here is we're putting a geologist into Argos in lunar gravity in a prototype spacesuit and having him go through a whole battery of tasks that future astronauts will be doing when they land on the moon, to do geologic sampling and other studies. In addition, we're also running him through a few various tests for getting up, doing a few other things with the spacesuit, as you can see right there. Harkens back to that Apollo video we showed at the beginning. And you can see here that we've set up a bunch of small little geology sites where we're using some of the same tool concepts that we're developing for the Artemis missions and learning how to use those in this relevant environment. And by doing that, we can really get a very firm idea of what these tool designs need to be, what the human performance is with those tools, as well as what type of metrics do we even need to measure to start redesigning those tools or redesigning the tasks to make sure we're being as effective as we can. And so this is this great ability for NASA where we're able to put an actual geologist and a planetary geologist into that real gravity environment, into a real spacesuit that's pressurized, and have someone who's an expert in that field in that high fidelity environment able to give real feedback to all of the engineers, all of the researchers, and all of the scientists who are working towards that mission. Which I think just goes hugely towards cutting down any risk to not getting the right samples, having a astronaut safety issue on the moon, anything that we could look at going forward. So really great to be able to get that into Argos. Finally, I've got a little hint of what's to come in the future. As you could see in that previous video, we had to use a lot of small sampling containers, a lot of small areas and treadmills. We're currently working on concepts for our next generation Argos, which we call the Argos Exploration EVA Simulator, or AXES, which will be a multi-crew offload system where multiple crew members can work in close coordination with each other over about 10 times the test volume of the existing Argos. So this is going to be a huge capability. The small sandbox that they're in is the same size as the Argos structure, just for reference. So you can see how much more capability that we're adding here. And we hope that this really turns into a fantastic spot to do a lot of future lunar and then Martian training, engineering development, spacesuit development, everything that we need to get along towards landing in those areas and conducting those missions. So hopefully this has helped show how we're using Argos today and where Argos is going in the future to really enable our astronauts to best train in the reduced gravity environments.
Wow, Paul, thank you. That was absolutely fascinating. And I love that imagery of the astronauts during the Apollo program stumbling on the moon. Talk about making a case for training and understanding how to move in different environments. Next, we'll hear from Jocelyn.
Hi, I'm Jocelyn. I'm a human performance engineer at NASA Johnson Space Center, and we are one of the customers of Argos that use Argos for some of our testing objectives. So first I'll tell you a bit about me and then how we've been using Argos. As I said, I'm a human performance engineer. That often means I'm in the control room running different tests with astronauts or other subjects in the spacesuit, running through next generation concepts for going back to the moon or even Mars. But occasionally I also get to be a guinea pig and part of the testing myself. In the middle there, you can see me in Argos suspended in a microgravity for some other testing. And then on the right was a suit fit check recently, my first time being in a spacesuit, a real spacesuit. And so hopefully one day I'll get to be in Argos in a spacesuit in the future. A bit about how I got here. I didn't even know the title Human Performance Engineer existed when I started out in school. I grew up in Florida. I was inspired by the space shuttles and NASA Kennedy Space Center to become an engineer. I went to Embry-Riddle Aeronautical University in Daytona Beach, Florida, and I studied aerospace engineering there. But even just in my first semester, I had some guest speakers from Johnson Space Center that were speaking about the human side of spaceflight. And I realized that was what I was really passionate about, and that's what encouraged me to go on to graduate school and focus more on the life sciences side of things. So I went to Purdue University for both my master's and PhD. That's in Indiana. So there I started in biomedical engineering for my master's, and then broadened a bit into industrial and systems engineering to focus more on the integrated system of humans. And actually through that program, I ended up getting to experience again firsthand what it could be like to be a future explorer through the high seas habitat that you can see pictured here. This stands for Hawaii Space Exploration Analog and Simulation. So we lived there for 8 months as a crew. We did simulated EVAs, and you can see a picture of me actually hitting a golf ball in the EVA suit, which was a really fun experience. Now moving on to what I'm doing today at NASA Johnson Space Center. Our lab, H3PO lab, focuses on spacesuits and exploration operations. We also have exercise physiology experts and applied injury biomechanics subject matter experts as well. Within the spacesuits and exploration ops technical area, we focus on developing pre-breathe protocols for getting into the lower pressure environment of the spacesuit, how to protect from decompression sickness. We also work on suit design and injury risk characterization. and different concepts for operation and task design, as well as informatics to support when we go on to distant destinations with communication delays. We're going to need more informatics and support for those missions. One of our primary projects is the physical and cognitive exploration simulations that works with Argos. There we simulate different tasks and try to make them as physically and cognitively realistic as possible. EVAs are a long duration activity, 6 to 8 hours in a spacesuit, and it's a very high risk operation, probably the most high risk thing except launch and landing, of course. So during this, they're doing complex procedures while fighting against the pressurized spacesuit, and we want to be able to test what are the limits of what humans can do in the spacesuit. Some of our testing on Argos has included developing some of the simulation capabilities that you'll see in the next photos and videos. One of our upcoming studies on Argos is called Egress Fitness. This will be the first time that returning crew from the ISS do a simulated EVA, and within 48 hours of landing back to Earth. Currently, when astronauts land back to Earth, there's a whole team there to rescue them from the capsule and extract them and do their medical evaluations. But when we go to Mars, that won't be the case. There will not be a team waiting to help them get out of the capsule and connect their habitats and get going. So we need to evaluate what the humans can do and how soon after landing. So we're tracking their pre-flight performance and comparing it with when they first returned back to Earth, and then also some other multiple sessions to see them recover back to baseline. And this can inform future concepts of operation for Martian missions to see what type of assistive devices we might need in order to enable astronauts to do those first EVAs on Mars. This is showing some examples here of the tasks that we're including in our lunar and Martian EVA simulations. There's a lander on the left that has a ladder that we can do the functional movements of climbing up and down out of a lander and going through a simulated hatch in and out of the lander. We have task boards that enable some simple fluid and electrical connectors, and also just different tools that you can interact with to simulate maintenance procedures. And then in the limited volume of Argos, to be able to simulate a longer traverse, we have a treadmill that can tilt to different inclines and declines to make a representative traverse along the surface in different levels of gravity. We've also been developing tasks for just looking at the capability of the human to traverse with different mass and volume of equipment. So you can see on the left a bag that's filled with about 25 pounds of weight, and so we vary that weight and also see how many trips back and forth that each crew member can make in a certain set amount of time. And this is one of our metrics that we'll be comparing pre and post flight to see any deconditioning or neurovestibular impacts that make this task more difficult for the returning crew members. With the advanced geology tools, it makes a big difference when you're in the pressurized gloves on the hand fatigue. So when the tool engineers have a new concept for something that we might use on the moon, they like to bring it to our suited tests, and then we can provide feedback and ratings of what type of fatigue they're encountering while using these tools in the suit and with the gloves. Another aspect that we're quantifying at Argos is the simulation quality of the offloaded environment. There's different options for the gimbal, which attach the suit to the Argos robotic crane. On the left, you can see the C-brace gimbal. In the middle is what's called the spreader bar gimbal. So we've been evaluating what the center of gravity, the different mass that we end up creating for each of these offloaded conditions, with one that's more massive and the other that's less. And then you can see the board there on the right is a way out board with 4 transducers where we can then see exactly where the center of gravity is in the different configurations. And this will help us to understand the fidelity of the operations. And when you're using a spacesuit with, this giant life support backpack, what does that feel like to the crew members, and how do we make sure that that is a representative center of gravity so they understand and can train with high fidelity without tipping over in the suit. This is a video showing some functional movements, and you can compare and contrast this with the other Apollo videos that Paul showed. So you can see with these prototype spacesuits, you can bend down and get back up much more gracefully. The Apollo suits didn't have a hip joint because they originated from just high altitude aircraft suits that were worn in the cockpit. But these advanced prototype suits do have hip joints that allow you to kneel down and get back up with a lot more grace and mobility. During the test events, we have some real-time physiological data that we're monitoring in what's called our HIPPO web application. This includes heart rate and metabolic rate. We also survey before and after runs for any injury potentials or any discomfort. And also on the cognitive side about how fatiguing the operations were, or how we can make sure that we are quantifying what that workload is and getting more and more high fidelity simulations as we continue to develop our tasks. You may have noticed in some of the videos there were little sensors attached on various segments of the spacesuit. These are inertial measurement units, or IMUs, and they allow us to track the functional movements of the suited subjects. And we're developing algorithms to be able to automatically detect when someone's walking versus standing still, bending down, getting back up. And this will inform our injury projects, so we understand what are some of the repetitive motions that astronauts will have to do to perform their work. And then that will inform our models for occupational surveillance about any potential injury impacts, say lower back strain or other aspects to watch out for injury potential. Here is showing the physical workload. This has heart rate and metabolic rate at the top. We're interested in metabolic rate in particular because it's a main predictor of suit consumables monitoring. So as you breathe in more oxygen and exhale more carbon dioxide, the suit has to provide for those inputs and outputs and process the human's carbon dioxide and provide that oxygen. And so that's our main predictor for modeling a lot of the suit consumables, including the water that feeds the cooling system. So with the next generation spacesuits, we're looking to optimize for human health and performance and make sure that we have enough cooling capability and different pacing strategies to make sure that the human doesn't overheat in the spacesuit. So in summary, we've been using Argos to develop simulations that have physically and cognitively realistic demands on the suited subject. This enables us to understand what type of consumables will be used to perform lunar tasks. And we want to optimize the performance of the human and figure out the correct pacing strategies to give time to rest and make sure that we're not outpacing the suit too much in terms of carbon dioxide and heat storage limits. And in all, we don't want to just keep the astronauts safe, but we want to actually optimize their performance and make sure that this entire system, from the tools to the suit design to the informatics that we can provide, enable them to be able to plan, make decisions on the fly, and support their health and safety, of course, throughout as well.
That is absolutely fascinating. Thank you so much, Jocelyn. And it's really so much and so intricate that to maintain someone well inside this environment. And so I'm also looking forward to our questions at the close of our conversation. And last but not least, I'm delighted to introduce Mike Foreman, our astronaut, to provide his perspective on astronaut training.
Well, thanks, William. I'm right there with you, listening to Paul and Jocelyn. I can't wait to hear what you ask them next. Save the hard questions for them, please. Definitely, I am not the smartest guy on this panel, I'll tell you that. But I was a kid growing up in Wadsworth, Ohio, always wanted to be an astronaut. Worked a lot of my career striving to get accepted into the astronaut program. In fact, I applied 8 times before I was selected by NASA in 1998. And when you initially come to NASA, you start doing what they call astronaut candidate training. So you're going to get the sense here in a minute that astronauts do a lot of training. So you start out in astronaut candidate training, you do that for about 1.5 years, and that entails things like Space Station 101, you know, the basics of space shuttle, space station. They're teaching us a little bit about astronomy and geology and all the other things that astronauts need to know a little bit of. And sometimes people ask me, well, you must know a lot of stuff. And I tell them, well, I know a little bit of a lot of things. My depth in a lot of areas is not that deep, but I do have a lot of breadth in the things that NASA has trained me. But you come out of astronaut candidate training, you're a full-fledged astronaut, you're waiting for that first mission assignment, but you continue to train. Even though you have a ground job now, and William mentioned early on that my first job after astronaut candidate training was I was the astronaut liaison to all the space station training facilities in the world. So I not only spent a lot of time in the building where Argos is, but I spent a lot of time in Russia, Japan, even Canada, where our partners have training facilities, and just keeping track of all the training facilities that they have and what they're doing with them and how our astronauts are doing in that training. So I spent a lot of time doing that, but meanwhile, you're continuing to train, waiting for that first space shuttle mission assignment. For me, as a space shuttle astronaut, I was waiting for my first assignment on a space shuttle mission. So I did advanced training like spacewalking and even operated some robotic arm things. Mostly my advanced training was in spacewalking, and people find out I'm a mission specialist and they ask me, what was your specialty? If you're a mission specialist, what is your specialty? And I say, well, NASA really never told me what my specialty was, but they let me do a lot of spacewalks. So I think EVA or spacewalking was my specialty. So I spent a lot of time in sort of advanced training, learning how to do spacewalk tasks and learning how to use the tools and doing a lot of that. So these first pictures are showing some of my astronaut cohorts using probably the precursor to Argos called Pogo, which was similar to Argos in that it suspended you, or it suspended an article, a piece of equipment to offload it so that you could maneuver your body around, find out what the reactive forces were going to be when you're trying to use your tool to turn a bolt. You want to find out what the forces on you are going to be, and you find out quickly that if I try to turn a bolt that's really too tight, the bolt's not going to turn, I'm just going to turn. And so you learn quickly about that, reactive forces. We spent a lot of time for spacewalk training in this world's largest indoor swimming pool that Paul had a picture of earlier, where we train underwater with the suits on. But you know, we couldn't do all this without all these folks that are helping us all along the way. It's not just get a bunch of astronauts together, tell them what they're going to do on their mission and expect them to go do it. It takes hundreds, if not thousands of people like Paul and Jocelyn to help us figure out what the best training device is that we can use for a certain skill that we need to learn for a task that we're going to do on the space station. So here we are. This is an underwater view. It looks like a spacewalk, but if you look in the lower left, you see a safety diver down there with scuba tanks. So that's actually in our pool. One of us in a suit working in an APFR, I think, there at the end of the robotic arm, which is what Paul also alluded to, the foot restraint that helps us react forces when we're out there floating outside the space station. Finally, getting to space, and this is just prior to my first spacewalk. That's astronaut Peggy Whitson there, who was the commander of the space station on my first mission, STS-123. And we had a really interesting task on STS-123 where we took up a contraption called Special Purpose Dexterous Manipulator. Dexter is what we call it. It's basically became a big hand for the end of the robotic arm on space station, but we had to take it up in 11 different pieces and put it together. So 3 of our 5 spacewalks on that mission had to do with putting Dexter together. And we used Pogo a lot, the precursor to Argos, in that we needed to do a lot of the tasks to figure out how we were going to communicate when we got to space. Dexter had 2 arms that we put together. The arms were 11 feet long, And one of us had to control one end of the arm while the other one connected it to the body of Dexter. So we used Pogo to support those 400-pound arms, and we stood on the ground. So in all those pictures you see astronauts are suspended. Well, sometimes the equipment is actually suspended. And we, using our feet firmly planted on the ground, we could figure out how we're going to communicate to each other about which way to rotate this arm or tilt it this way or that way to get the pins to line up, because the Canadians that built Dexter had a pin mechanism to attach these arms, and if the arms wasn't perfectly aligned with the body, the pins wouldn't go in. And so we used these tasks at the Pogo to teach us how to communicate back, because you just can't say in space, hey, tilt it to your left, because that might not be the right direction. So we had to come up with certain schemes, reference planes, and so forth to coordinate all that and be able to do the task. And ultimately in space, we went outside and we put Dexter together, and Dexter is still up there operating when space station astronauts need it. The picture here that we're looking at is the pallet, which is really a cup-shaped platform that all of the Dexter components were attached to, and we went in there and worked on each of these spacewalks, taking the pieces off the sidewall and attaching them to the body of Dexter, and finally getting that all together. During that attachment, one of my jobs was to just be sort of a human holder for one of the arms while my partner on that spacewalk, Rick Linehan, was getting into position so that he could raise the body up. Dexter's body rotated up out of this platform while it was still attached there, and we had to get into position and use those same communication skills to put the arms in the right position to attach them to the body. Another task we did, which we trained for down here on Earth quite a bit, was to install this boom arm onto the outside of the space station. We took this boom up in the payload of Endeavour when we launched, but each space shuttle mission needed this boom to inspect its undersurface after launching, make sure we didn't have damaged tiles. But the mission after ours had such a large payload that they didn't have room to bring the boom up. So once we finished our inspections, my partner Bob Benkin on this spacewalk and I attached the boom on the outside of the space station. And all these tasks, it's not something that you just go to space and do for the first time. We're rehearsing these things hundreds of hours, hundreds of times down here on Earth, and all these different training environments that my predecessors in the panel have talked about, Pogo, Argos, and Paul and I actually worked on Argos together. We were talking earlier, we realized we worked together a little bit in 2013 after my space shuttle missions, and we were over there doing a test on another program. There's my hero shot. Yeah, you know, big strong arms in this suit that's difficult to work in, like Jocelyn said. I'll let it go at that and give you some of your time back, William.
Thank you, Mike. That is absolutely fascinating. You know, it's clear that it's very dangerous doing spacewalks, and so many things can go awry, and that training is essential to affect something, you know, well. And I think also the average spacewalk can be 6 to 8 hours, and if something goes awry, it can be even longer. So it requires an incredible amount of stamina. So I guess I'm curious to hear from Paul and Jocelyn, how do you determine how much training, say on Argos, is required for an astronaut to prepare adequately for one of these repairs, like the alpha magnetic spectrometer?
That's a great question. So that's a very detailed discussion at the mission planning level and the crew training level to really understand what are the tasks that need to be trained, and then what are the milestones and the metrics that you need to go through to get confidence in that. So for AMS, for example, you know, so much of it was just learning the body positions, learning the reach access that the astronaut had, learning all the little quirks of using those tools. And as the training for AMS and the development for AMS went on, we added more training events and more development events in Argos to make sure that we were adequately training for that and adequately developing it. So it's really, you know, from my perspective, where I'm not making the decisions of when they're ready, it's always, you know, whatever it takes to get to the point that they are ready.
I think, like Paul said, these outstanding individuals provide these excellent tools for us to use. We go in there with our training team and our training team includes instructors, includes the people that are actually going to be sitting there on the console and mission control while we're doing these particular tasks. All the astronauts that are going to be involved, not only the two that are outside doing a particular task, but the astronaut that will be inside the space shuttle or the space station talking to those astronauts. And I think we realize what we need to learn sort of in our heads a lot of times beforehand, and we go in, and of course a lot of these situations we have these aha moments where, wow, there was something that we just learned that I didn't even think we needed to know. You know, sometimes you don't know what you need to know ahead of time, but a lot of times we kind of go in with a feeling on this is what we need to get comfortable with. And in my case with Dexter's arms, we supported those with pogo so that we could maneuver them around. They're 400 pounds, so we couldn't just twist them around down here, you know, between the two of us. We needed them supported, and we needed to figure out a communication strategy so that we could get those things lined up. And so I think at the end of the day, a lot of times we and our training team go, okay, Mike, you got it. And I say, well, maybe we could go over it one more time, try it this way one more time. And then, yeah, I got it. And then we move on and maybe to the next, maybe an NBL run where we're underwater now testing out those same communication protocols with the actual hardware underneath in the water. But water is not always a perfect environment. It wasn't for Dexter's arms because the arms underwater kind of wanted to flip a certain way because they had some buoyancy issues. So pogo was a great place to do that. And so I think a lot of times, yeah, it's they provide these great devices for us and let us play on them and make sure we don't get hurt. But our training team sort of figures it out. Okay, I think we can move on to the next stage of the training.
So Jocelyn, I'm curious, what role do you play, or do you play a role in developing the tools? So you think about the alpha magnetic spectrometer, the AMS, and God, that was a $1 billion value piece of equipment that's looking at particle science and looking for dark matter. I mean, it's an incredibly important experiment. And so of course we want to keep that technology functioning on station. So do you play a role in looking at the tools? Because you just can't go to Home Depot and pick up a wrench or a drill, right, to function in space.
We do work closely with the tools engineers and engineering. However, we're not the ones designing the tools. What we can provide a lot of the time on the human health and performance side is the workload associated with using various tools. So once the engineers have designed a prototype and they bring it over for testing, we can monitor heart rate, metabolic rate, and understand the workload, and also collect ratings in a structured way about any fatigue that may be coming up when using a tool. It could be localized to, let's say, a bicep or their hand. So we're often collecting that structured information about the physical workload and fatigue as it comes up when using these prototype tools.
Well, I'm also curious, I'm fascinated by the spacesuits because the spacesuits basically are spaceships, right, on your body. They have to maintain all your body systems, keep you alive. And I'm curious from all of you to say, do you actually inform spacesuit design? Mike, you've been in a spacesuit, you know, and done spacewalks. And I know because they're pressurized, they're really rigid. Do you, when you come back to Earth, debrief and give advice on design? And do you, and for Paul and Jocelyn, you're training with astronauts and other experts. Does your research, the work you do in training, also inform spacesuit design and changes to the design of the suit?
Well, most definitely, we come back and we are in those suits a lot down here on Earth too, because in the pool where we're training, we're wearing the same suit essentially underwater for 6 hours, 7 hours a day when we're training. And so we spend a lot of time, and we know, of course, we sort of start to figure out how to work in the suit. And my test pilot background would say that we're compensating for the quirks in the suit. We're making up for the deficiencies in the suit that we have. But of course, that suit that I wore in space was a marvelous engineering design. Like you said, William, it's a one-person spaceship. You don't really put it on. You get into it, and then you float outside. It provides the oxygen, the cooling, the CO2 scrubbing, the radios, so we can talk to each other. all that stuff, the lights, so that we can see in the dark. It's a great marvel. Yeah, we come back and we say, wow, I actually, got a shoulder injury from working in the suit, and so we more astronauts than one have had injuries from working in that suit. But we learn, hey, how to maneuver around the problems that the suit has, and we're always talking to the designers of the new suits about, hey, could you make this better? Could you make these shoulder joints a little more flexible so that we don't have these injuries, and doing things like that all the time. But I know Jocelyn and Paul as well have had inputs like that as well. And they've both been in the suits too, so they can tell you.
On the human health and performance side, we're often informing requirements for the spacesuit design. So these requirements, they can get into very small details, from whether it's the cooling that is needed in order to make sure that the human isn't overheating, to the humidity levels, to make sure that we're not in a too dry or too moist environment. So we develop standards and continue to update those, and that feeds right into the design. Some of them are also more related to the ventilation, for example. So as you breathe out your carbon dioxide, as you respirate and as you work harder, we need to make sure that the ventilation is washing out the carbon dioxide. And we also help develop medical requirements for exposure limits to carbon dioxide that are monitored during training and flight to make sure that we're not getting too much exposure to elevated CO2. So through the requirements definition, that's a important phase, but then also as we develop the new designs to make sure that we are validating that we have met those requirements. And so that's when testing on Argos comes into play, where we have this set of requirements, and then we're now checking off the boxes that we're able to meet those. So that's primarily how we play a role in suit design, is on the requirements verification side.
And over on Argos, fortunately, we don't have to help design the suit because it's incredibly complicated. And the suit engineers and suit designers doing that are just amazing in what they're working on. But what we can do is try to make sure we're providing a really good reduced gravity environment and work closely with them to understand what upgrades we need to make to, for example, our gimbaling system, on how we connect you to Argos so that they're getting realistic data out. We're not impeding the suit. One of the things we've had, for example, with an earlier gimbal design was when you went to move your arms this direction, you touched the gimbal. And so now you actually can't even test the mobility of the shoulder joint of the suit because Argos is limiting you. So we work closely with them to make sure that we're minimizing those with Argos, so then they can use our system to best design their suit.
Oh, that's fascinating. So I'm curious, we're returning to the moon with Artemis. It's coming up pretty soon in about 3 years. Is Argos currently being used to begin doing testing preparation for the Artemis astronauts?
So with Argos today, we are mostly doing development and research studies. Since we don't have a crew selected at this point for the first landing, we're not doing any active training for Artemis, but we are working extensively with the spacesuit developers, with the tool developers, with Jocelyn and her team to best set ourselves up to be in a position for that. So evaluating all the tools, evaluating the spacesuit, and as Jocelyn talked, taking all of that human performance data to inform the requirements, inform the design, and inform the planning for those EVAs.
Yeah, right now it's in a kind of fun phase where we're trying to play pretend moon again and develop all of the mock-ups and tools and things that we need to simulate being on the moon. So that includes like the lander mock-ups, and now we're getting closer to understanding what the human landing system design might be, but we had to, just come up with representative lander mock-ups to start. And as we start to know more about the different assets that'll be on the surface, we can create higher and higher fidelity simulations in Argos but it's a very iterative and dynamic time for us right now. And we're trying to evolve as we learn more and more about the hardware itself. And then also at the same time, stay ahead of it a bit and evaluate some of the unknowns. So for example, with the ladder, we did some preliminary evaluations to see what would be a good step height, you know, as we're looking toward different lander designs. Should it be, you know, 1.5 feet and reduced gravity? Can you go a little higher, bigger steps? So trying to optimize and come up with, again, requirements or guidelines that can inform the best design as we are working toward getting back to the moon.
So I'm curious because I'm fascinated by Artemis. This is coming up pretty soon. And the architecture for this mission is very different, right? Where they're talking about possibly using Gateway as an intermediary platform, but then also long duration on the surface of the moon. So as you're modeling and looking at potential training for astronauts, are you exploring that option of someone? The Apollo program was really about going to the moon and coming back, right? Very much that we could achieve that, bringing some samples, but the main focus was not on the science, where the Artemis program is really about the science. Is there water at the South Pole that can be rendered potable and perhaps used as fuel if it could be broken down into its elements? Are those things that you're beginning to explore as part of the training, preparing astronauts potentially to be on the surface for many months and be conducting active science?
The very first Artemis mission is set to be kind of similar to the Apollo style, and even that is a little bit of a stretch compared to what we do today. It's going to require crew to do 4 EVAs in a 5-day time period. That back-to-back EVA cadence is not something we routinely do anymore, so not since Apollo, and even then I think there was only a maximum of 3 EVAs in one mission during Apollo, and so that workload and fatigue of doing back-to-back EVAs is something that we are beginning to study and developing research studies surrounding that. As far as the training paradigm, it will most likely have to shift in order to make sure that we can do those repetitive exposures to the suited environment. A lot of things can come up. Even something as simple as a blister can be a game stopper in terms of performance if that happens on the very first EVA and gets worse over time. Right now, I believe crew space out their training events with at least 7 days between NBL suit exposures to make sure that you don't aggravate those type of minor injuries and give yourself time to heal in between. So going back to the moon and having a sustaining system where we need to do that quantity of EVA is a real paradigm shift for the program.
So Mike, I'm curious, because you have done many hours of spacewalks, how do you in your training prepare yourself for that kind of physical rigor of being in this environment for hours and hours and hours and knowing that you got to get the job done right while you're out there? It's not like you can say, I want to take a break, I'm going to go in and rest for a little bit and come back out again. How do you physically prepare yourself for the rigors of a spacewalk? Well,
I think the best training for the spacewalks that I did was the pool training, the NBL, when we were underwater in the pool for 6 hours at a time, working in essentially the same suit that we're going to be working in space. But we also have the water resistance underwater. So every time we move ourselves, every time I translate on a set of handrails on the outside of the space station, I'm moving my body against all this resistance. And so you build up the muscles, all the muscles above my chest and my arms and shoulders were just totally fatigued at the end of one of those training days. And after you've done about 100 of those training days, which I've probably done in my career, your endurance and your muscles are built up to the point where they can last for those 6.5 or 7 hour spacewalks in space where you're not working against water. There's absolutely no resistance up there at the space station. There's it's a vacuum. So you are not working. In fact, you have to slow down a little bit in space, because if you try to move yourself with as much force as you're moving yourself in the pool, you'll kind of go out of control, and it wouldn't be good. So I think the training really builds up all those muscles, all the endurance for that. But listening to Paul and Jocelyn talk about all this stuff that's going on over there is making me tired, just listening to it, because I'm reliving those days in my mind where I would just come out of a training session totally beat, and looking forward to a good night's rest. And in space, I never did 2 back-to-back spacewalks. We always had at least 1 day in between spacewalks to recover, and that was a good thing. Between my second and third spacewalk on my first mission, like Jocelyn was saying, I developed, I had a problem with my left hand. My glove fit wasn't the best, and unfortunately on that mission, I went through 2.5 pairs of gloves because we were very concerned. We had just previously had some astronauts come back inside with cuts in their gloves. So we were very sort of slanted towards being extra careful. And after each spacewalk, they would look at your gloves. We would take pictures of the gloves after a 6.5 hour spacewalk, and the engineers on the ground would decide if we could use those gloves again, depending on how beat up they were. And in my first 2 spacewalks, they said, no, use your backup gloves, then use your second backup gloves. And I think my first set of gloves really fit well, and my second pair and my third pair didn't quite fit as well. So by the end of my third spacewalk on STS-123, my left hand was sort of in agony, and I was looking for reasons to cut that spacewalk short. Frankly, we got everything we were supposed to do done in a little under the 6.5 hours we had planned to do it. And they said, hey, do you guys want to stay out there and maybe do a couple of extra things? And I said, I vote no. I was ready. My hand was sort of throbbing. So it's little things like that will really set you back, and you don't really think about them that much. You just think, well, the suits probably fits perfectly, and it doesn't always. It's going to be these little issues that'll kind of reach out and bite you.
Well, I think in the end, we're only human, right? And so, we're actually pretty fragile organisms, and it's remarkable that we have developed these strategies to go out into space in this environment that a lot of people say are trying to kill us in many different ways. Yet we find a way to explore it. Paul, I'm curious, you in your presentation gave a great background on Argos and how it's evolving, but you also gave us a sense of the future Argos. And it appeared that it could manage more than 1 astronaut or astronauts and equipment. So what is the purpose of having multiple individuals participate on or train on an Argos system as opposed to a single individual?
So you'll notice in spacewalks on the space station, for example, it's always 2 astronauts going out together. Apollo, always 2 astronauts. Artemis is going to be multiple astronauts. Astronauts are never doing their spacewalks alone. They're always working together, always tackling problems together, doing things jointly, oftentimes touching the same thing at the same time, where they have to be very close to each other. And so what we need to really train the best for these spacewalks is to have both astronauts be in simulated reduced gravity in close proximity, so that they can do that just like they will on the mission. With Argos today, we're only capable of offloading 1 of the astronauts at a time. And so what happens is you have the second crew member standing there on the ground alongside of them, or laying down on a surface or something, just trying to be in the right spot. But they're not in any simulated reduced gravity. So their training isn't anywhere near as realistic and as powerful, and can, if taken to the extreme, could sometimes lead to getting false training or negative training because you don't understand the interaction of the 2 astronauts working together. So especially as we go towards landing on the moon and doing geology sampling, setting up work sites, all these things that you expect to have 2 astronauts having to be a very big part of, we really do need that capability. So we're designing that from the start as one of the key features of the new one.
Wow, that is absolutely fascinating. That's going to be quite exciting. Will it have the capability of having equipment attached to, say, one of those mechanisms? So if I know, for example, with the AMS, I go back to that, and you show the video of Luca Parmitano training on that. Was the model, the tool he was using, also on the Argos? Were they two different Argos systems to try to replicate as closely as possible the situation he would have been in?
So for the our concept for the next Argos for Axes, we're actually installing 3 offloading systems that can work closely. And the goal is that way you have 2 astronauts plus equipment. And you can always be offloading. Unfortunately, since we're like a crane, you can't cross since you're being suspended by a cable. So we do have to get the test area set up properly, knowing that astronaut A and astronaut B can't cross paths on that long axis of the structure. So set up the equipment properly and all those things. But we do intend for that. On AMS, we generally did not offload the tools because they were fairly light in the scheme of things, a couple of pounds. And what we would do is, as the astronaut would grab the tool from the other astronaut or from a trainer, our operators on Argos correspondingly add or remove that amount of offload from Argos, so that the astronaut is still in microgravity now holding that couple of pound tool. So before the test ever begins, we go through and weigh everything that they might be touching that day. We load it up in a list on our operator GUI, our user interface, and that operator is standing by to add and remove those tools as they're handed to that astronaut. But occasionally we do use a separate passive offloading system using what's called constant force spring motors, which are more similar almost to like a tape measure and the spring retraction of that. And we'll set that up on a rolling stand that comes in and tune that in for the tool that they're going to be using. For heavier tools like the PGT, or sort of their electric screwdriver that they use, which weighs a decent amount of weight, so it's very tiring for them to use in Argos and 1G. And then we'll sling that to that tool, so that secondary system's offloading it, and then they're being offloaded by Argos.
So I'm curious, because I know that Johnson Space Center has done a lot of work with robots and robotics and robots supporting human missions. I'm curious, Jocelyn, are you involved at all in the robotic support of training with in human factors or Argos? I mean, we see when we go over to Johnson, they now have Robonaut 5, and Robonaut 5 is being developed and adapted for many different uses. But one idea is that it could support creating habitats or putting habitats together for humans. So I'm just curious, are you doing any research or work on human-robot interactions?
Unfortunately, no, I haven't had any projects. That's definitely a very exciting area of research. I think some of our colleagues in the Human Factors Engineering Lab may work more closely on the human-robot interaction, but unless you can consider human spacesuit interaction robotic, I don't know, that would be the closest I've come so far.
I would count that. I think that's absolutely true, right? It's you know, we may have these notions of robots being these autonomous things, right, that do things, but really it's anything robotic, right, that supports us in some way. Well, we're coming to the close of our time, and this has been so much fun speaking with all of you and been so insightful. And I wanted to give you a chance to share any kind of final thoughts about the Argos system and its role in advancing human space exploration.
You know, for Argos, we're just really excited with how we're able to be a crucial part of all of our development and crew training. You know, for Argos was developed at the Johnson Space Center in our robotics division, in our engineering directorate. So for all of us, you know, it's a really fun robot, and to have the chance to make a robot that then goes on to enable our astronauts to go off and do their missions and do their missions safely is really rewarding for all of us there in robotics.
Likewise, on the customer side of Argos, we're so thankful that we have this capability to be able to rapidly test and improve our support for human health and performance in the spacesuit. Argos has enabled us to collect a lot of early data to support suit design and requirements definition, and it'll go on to improve training and get astronauts ready for going back to the moon.
Yeah, and I hope people watching this will realize that if they didn't know already, that the Johnson Space Center is the home of the U.S. Astronaut Corps. It's where just about every bit of astronaut training happens. And without people like Paul and Jocelyn and about 1,000 other people, astronauts would not be able to get trained to go do these missions as well as we're able to do them. And I tell you, if we had to do these tasks the first day without all this help, they wouldn't come off as well. I know that. So thanks to Paul and Jocelyn and all those other folks. You know, it was good. It was like old home week watching your video and your slides, Paul, especially. I see Oscar Kaler and some other people that I know, Luca, of course, Drew Morgan. Anyway, it's great to be a part of this, and I hope I contributed just a little bit.
Great. Well, listen, thank you, Paul, Jocelyn, and Mike, for this insightful conversation, your excellent presentation. It was absolutely fascinating. And I want to thank all of you for joining us for the Thought Leader Series presented by UTMB here at Space Center Houston. Please tune in for our future programs. All of our programs are archived on our website at spacecenter.org. Again, thank you for joining us.